A single radio signal from deep space screamed for 72 seconds and vanished forever. That is the edge of our understanding, a place where the universe's rulebook seems to have missing pages. Today, we are venturing into that unknown, counting down the top 25 astronomical phenomena that still baffle the brightest scientific minds on our planet. By the end, you will have a front row seat to the greatest unsolved mysteries of the cosmos, from phantom forces tugging at spacecraft to a star that dims in ways nothing natural should allow. What does it mean that our galaxy is being pulled towards something we cannot see, or that the ancient afterglow of creation itself might be pointing at us? The answers are not in any textbook because we simply do not have them yet. What cosmic puzzle do you think defies explanation the most? That 72-second burst of radio waves has a name, the WOW signal, and it arrived in the dead of night on August 15, 1977. The Big Ear radio telescope at Ohio State University was silently scanning the sky, its data printed on long sheets of paper covered in letters and numbers. Astronomer Jerry Amon was reviewing the readout days later when a sequence of characters leaped off the page, a spike of intensity so strong and so unusual that he circled it in red pen and wrote one word in the margin: "Wow." The signal was not static or noise, it was a pure, narrowband radio wave, a focused whistle in the cosmic static. Even more compelling was its frequency. It hit precisely at 1,420 MHz, which is the natural radio frequency emitted by hydrogen, the most common element in the universe. It is often considered a logical channel for any civilization trying to announce its presence, a cosmic waterhole where messages might be left. For 72 seconds, as the Earth's rotation swept the telescope's gaze across that patch of sky near the constellation Sagittarius, the signal blared, then it vanished. Every attempt to find it again with more powerful instruments over decades has met with total silence. One leading theory suggested it might have been a reflection from a passing comet, but that was later carefully examined and largely dismissed. The comets were not in the right place at the right time. So we are left with a haunting possibility, a one-time shout into the dark from a source we may never identify. Was it a natural cosmic event we still do not understand, or was it something else, a fleeting hello from across the stars that we heard once and may never hear again? The WOW signal remains a perfect, solitary question mark, a reminder that sometimes the universe speaks just loud enough for us to hear, but not long enough for us to understand. That solitary WOW signal was not a cosmic fluke, but perhaps a whisper of a far louder and more chaotic phenomenon. Scattered across the universe are cosmic explosions so powerful they outshine entire galaxies for a fleeting instant, yet they last less time than it takes to blink. These are fast radio bursts, and they represent one of the most energetic and perplexing mysteries in modern astronomy. The first one was discovered by accident in 2007, buried in old data from the Parkes Radio Telescope in Australia. It was a single, brilliant spike of radio energy that had traveled for billions of years, carrying more power in 5 milliseconds than our Sun releases in 80 days. For years, astronomers debated if it was even real or just some local interference from a microwave oven on the observatory grounds. But then more were found, each a spectacular flash of radio light from a random point in the distant cosmos, each one vanishing almost as soon as it appeared. The true puzzle began when we found they were not all the same. Most are one-off events, a catastrophic cosmic firecracker that goes off once and is never seen again. But a handful, like the famous source known as FRB 121102, repeat. They send out bursts sporadically, sometimes in frantic clusters, sometimes with long periods of silence in between. This repetition is a crucial clue because it rules out any theory involving a single, total destruction event, like a star collapsing into a black hole. So what cosmic engine can produce such unimaginable power on a millisecond timescale and do it over and over again? The prime suspect today is a type of stellar corpse called a magnetar. Imagine a neutron star, an object so dense a teaspoon of its material would weigh 1 billion tons, but then twist its magnetic field to unimaginable levels, trillions of times stronger than Earth's. A starquake on the surface of such a monster, a sudden cracking of its crust, could theoretically unleash a focused blast of radio waves fitting the profile of a fast radio burst. Other ideas involve clumps of material falling onto a black hole or the violent mergers of neutron stars, yet no single theory neatly explains every observed property: the staggering energy, the split-second duration, the bizarre repeating patterns, and the fact that some seem to come from relatively calm regions of space devoid of the usual cosmic violence. Fast radio bursts are like finding scattered, ultra-powerful radio lighthouses flashing across the universe, but we have no map to tell us who built them or why they are flashing. While fast radio bursts are brilliant, fleeting mysteries, there exists a far more profound and pervasive enigma, one that forms the very scaffolding of the cosmos itself. This is the puzzle of dark matter. Unlike a sudden flash of light, dark matter is a silent, invisible presence that we cannot see, touch, or directly measure. Yet we know it must be there because the universe as we know it would simply fly apart without it. The first compelling clue came not from deep space but from the careful study of our own galactic neighborhood. In the 1930s, astronomer Fritz Zwicky was observing a cluster of galaxies and noticed something bizarre. The individual galaxies were moving so quickly that the visible mass of the cluster, all the stars and gas we could see, was not nearly enough gravity to hold them together. The cluster should have torn itself apart eons ago. He proposed the existence of what he called Dunkel Materie, dark matter, an unseen mass providing the extra gravitational glue. Decades later, Vera Rubin provided the definitive evidence by meticulously mapping the rotation of spiral galaxies. She found that stars at the outer edges of these galaxies were orbiting just as fast as those near the center. According to the laws of gravity as we understand them, this should be impossible. The visible disk of stars and gas simply does not contain enough mass to generate the gravity needed to hold those fast-moving outer stars in their orbits. The only logical explanation, a massive, invisible halo of something enveloping each galaxy, exerting a gravitational pull but emitting no light. We see this shadowy influence everywhere, in the way massive clusters of galaxies bend light from more distant objects behind them, an effect called gravitational lensing that acts as a cosmic scale, revealing far more mass than is visible. We see it in the very large-scale structure of the universe, the great cosmic web of filaments and voids that galaxies are arranged along, a pattern that could only have formed with the help of this unseen gravitational framework. So what is it? We know what it is not. It is not clouds of normal gas, we would see that. It is not a population of black holes. Extensive searches have ruled that out as the primary component. The leading candidate for decades has been a hypothetical particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy, slow-moving, and, as the name suggests, interact with normal matter only through gravity and perhaps the weak nuclear force, making them incredibly difficult to detect. This is why scientists have built exquisitely sensitive experiments a mile underground, in old mines and beneath mountains, to shield them from cosmic rays, hoping to catch the exceedingly rare ping of a dark matter particle bumping into an atom in a vat of ultra-pure liquid xenon. Others hunt for indirect signals in space or try to create them in powerful particle colliders. Yet, despite decades of searching, the detectors remain silent. We are surrounded by an ocean of something that makes up roughly 85% of all the matter in the universe, shaping everything we see on the grandest scales, and we have no idea what it is made of. It is the ultimate cosmic ghost, felt only by its gravitational hand on the shoulder of the visible world. If dark matter is the invisible scaffold holding the cosmos together, dark energy is the phantom force trying to rip it all apart. It is the even more baffling counterpart, a repulsive pressure woven into the fabric of empty space itself, and its discovery turned our understanding of the universe's destiny completely upside down. For most of the 20th century, scientists believed the expansion of the universe, set in motion by the Big Bang, was gradually slowing down due to the relentless pull of gravity. It was a cosmic tug-of-war, and gravity was expected to win. Then, in the late 1990s, two independent teams of astronomers made a shocking observation. They were using distant stellar explosions called Type Ia supernova as cosmic mile markers. These supernovae have a known intrinsic brightness, so by measuring how dim they appear from Earth, you can calculate their distance. By also measuring how much their light is stretched or redshifted, you can determine how fast the universe was expanding when that light was emitted billions of years ago. The results were unequivocal and astonishing. The most distant, ancient supernova were fainter than expected, meaning the universe is expanding faster today than it was in the past. The expansion is not slowing down, it is speeding up. Some unknown force is pushing galaxies apart with ever-increasing vigor. This revelation earned the teams the Nobel Prize in Physics in 2011, and the mysterious force was dubbed dark energy. Conceptually, the simplest explanation is a return to an old idea from Einstein, the cosmological constant. This is not a substance, but a property of space itself, a constant energy density that causes empty space to exert a kind of negative pressure, a repulsive gravity. As the universe expands and more space comes into existence, more of this repulsive energy appears, leading to an accelerating expansion. The scale of its dominance is staggering. Current measurements suggest dark energy makes up about 68% of the total energy budget of the cosmos, with dark matter comprising about 27%, leaving all the stars, planets, gas, and dust we see and are made of as a mere 5%. This has profound and frankly chilling implications for the ultimate fate of everything. If dark energy remains constant, the acceleration will continue forever. Galaxies outside our local group will eventually be pushed so far away that their light can no longer reach us, leaving our night sky dark and empty for any future civilizations. This is the Big Freeze, a cold, lonely, and eternal expansion into darkness. But if dark energy grows stronger over time, the outcome is far more violent, a scenario called the Big Rip. In this model, the repulsive force would eventually overcome all other forces, not just flinging galaxies apart, but tearing apart galaxies, then solar systems, then planets, and finally ripping apart atoms themselves at a finite moment in the future. Yet the deepest mystery is not just what dark energy does, but what it fundamentally is. When physicists try to calculate the energy of the vacuum of space using quantum field theory, their predictions are off by a factor of 10 to the power of 120, a number so unimaginably large it is often called the worst prediction in the history of science. This is the vacuum catastrophe. It means our two most successful theories, quantum mechanics and general relativity, are giving us answers about the basic nature of reality that disagree by 120 orders of magnitude. Dark energy is not just a puzzle about the fate of the cosmos. It is a glaring sign that we are missing something fundamental about the very nature of space, time, and nothingness itself. The accelerating expansion of the universe is a force acting on the grandest canvas imaginable, but sometimes the most telling clues come from the smallest discrepancies much closer to home. For decades, two robotic explorers on their way out of our solar system sent back data that contained a tiny, persistent whisper of something wrong. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were triumphs of engineering, the first human-built objects destined to leave our planetary family forever. As they journeyed beyond the orbit of Pluto, scientists meticulously tracked their trajectories using the Doppler shift of their radio signals. By the 1980s, an anomaly had emerged. Both spacecraft were slowing down slightly more than they should have been. It was an almost imperceptible effect, an unmodeled acceleration toward the Sun, equivalent to just 10 billionths of the gravity you feel standing on Earth. But over years and billions of miles, that tiny tug added up, pulling the Pioneers off their predicted courses by hundreds of thousands of miles. This was the Pioneer anomaly, and for years it haunted the corridors of physics. Could it be a sign that our understanding of gravity itself was incomplete at these vast interplanetary distances? Some proposed modifications to Einstein's theory of general relativity. Others wondered if it was evidence of unseen, diffuse dark matter dragging on the spacecraft. The mystery deepened because other distant spacecraft, like the Voyagers, did not show the same clear effect, though their trajectories were harder to measure with the same precision due to their different designs. The Pioneers became the most precisely navigated objects in the outer solar system, and their stubborn deviation was a constant, quiet challenge to our models of reality. The solution, as it turned out, was not in the laws of physics, but in the mundane reality of heat. A small international team of researchers embarked on a monumental detective effort, recovering decades-old design documents, telemetry data, and even original software to build a complete thermal model of the spacecraft. The Pioneers were powered by radioactive plutonium pellets, whose decay generated both electricity and a substantial amount of waste heat. The spacecraft were designed to radiate this heat away into space to prevent overheating. The team's painstaking analysis revealed a critical detail. This heat was not radiating away perfectly evenly. A tiny anisotropy, a slight asymmetry in the thermal radiation, was occurring. More heat was being emitted from the back of the spacecraft's main dish antenna, which faced toward the Sun, than from the sides. This imbalance created a minuscule but constant recoil force, a gentle thermal pushback toward the Sun, exactly matching the observed anomalous deceleration. It was not a new force of nature, it was the spacecraft literally pushing itself off course with its own warmth. The resolution of the Pioneer anomaly is a profound lesson in humility and precision. It shows how the relentless pursuit of a discrepancy, no matter how small, can lead to a deeper understanding of our own tools. What seemed like a crack in the foundation of physics was actually a masterclass in systematic error, teaching engineers to account for every photon of heat when planning the trajectories of future deep space missions. It reminds us that sometimes the universe is not the source of the mystery, our own incomplete perspective is. Yet it also raises a tantalizing question: if such a tiny effect from our own technology could mimic a revolutionary discovery, what other subtle whispers in our data are we still misinterpreting? The gentle thermal nudge that misled us with the Pioneer probes taught us to question every assumption, but some anomalies refuse to be explained away by our own machinery. When spacecraft swing by Earth to steal a little of our planet's orbital energy, a well-understood maneuver called a gravity assist, their speed should change by a perfectly predictable amount. Yet on multiple occasions it has not. This is the flyby anomaly, a tiny, stubborn hiccup in the flawless mathematics of celestial mechanics. The first clear case appeared with NASA's Galileo spacecraft in December 1990. As it whipped past Earth to gain momentum for its journey to Jupiter, ground stations tracked its velocity with extreme precision. When it emerged from Earth's gravitational embrace, it was moving just a few millimeters per second faster than all the complex equations said it should. This was not a large error, but in the hyper-precise world of orbital dynamics, it was significant and entirely unexpected. The anomaly popped up again with the Rosetta Comet Chaser during its Earth flyby in 2005 and with the Messenger probe on its way to Mercury. Each time, the spacecraft gained a tiny, unplanned boost, as if Earth's gravity gave it an extra, invisible push on the way out. Scientists immediately scrutinized every conceivable conventional cause. Could atmospheric drag have somehow sped it up? No, that always slows a craft down. Was it an error in modeling Earth's uneven gravity field? Teams used our most detailed maps of the planet's mass distribution, and the discrepancy remained. One intriguing idea pointed to an exotic relativistic effect called frame dragging, where a massive rotating body like Earth literally twists the fabric of spacetime around it, subtly altering the path of anything moving nearby. While this effect is real and has been measured around Earth, its magnitude is far, far too small to account for the flyby speed boost. The most baffling aspect is the anomaly's inconsistency. It does not happen with every flyby. The Juno spacecraft's Earth flyby in 2013 showed no anomaly at all. This suggests the effect might depend on the precise geometry of the encounter, the latitude of closest approach, or the inbound versus outbound trajectory of the craft relative to Earth's rotation. That selective nature makes it even more puzzling, as it hints at a physical cause we have not yet parameterized, a hidden variable in the gravity assist equation. The flyby anomaly stands as a quiet caution in the age of precision spaceflight. We use gravity assists as a routine tool to send probes across the solar system, relying on Newton and Einstein's laws as an exact cosmic clockwork. Yet here, at our very doorstep, that clockwork occasionally ticks out of rhythm by a minuscule but measurable amount. It is a reminder that even our most trusted models might have blind spots, and that the universe might still hold subtle secrets about how mass, rotation, and motion intertwine in ways our textbooks have yet to describe. The subtle nudges on our own spacecraft hint at hidden complexities, but a star 1,500 light-years away presents a mystery of such dramatic scale it defies all ordinary explanation. This is Tabby's star, officially catalogued as KIC 8462852, and its strange behavior was spotted not by a lone astronomer, but by the keen digital eyes of thousands of citizen scientists. The Kepler Space Telescope spent years staring at a patch of sky, monitoring the steady glow of distant stars, watching for the telltale, periodic dips in brightness that signal an orbiting planet crossing the star's face. These transits are usually small and clockwork regular, a drop of perhaps 1% that repeats every few days or months. Tabby's star did not play by those rules. Its light curves, the graphs of its brightness over time, looked like nothing else in the database. The star did not dim by a tiny, predictable fraction. It plunged into darkness by staggering amounts, up to 22%, as if something colossal was drifting in front of it. Even more bizarrely, these dips were completely irregular. There was no pattern, no predictable schedule. The star would dim dramatically for days, then return to normal, then dip again months or years later in a completely different shape and duration. A single planet, even a gas giant the size of Jupiter, would only block about 1% of a star like this. To cause a 22% blackout, you would need an object nearly half the width of the star itself, an impossibility for any normal planet. The hunt for an answer began, and the theories ranged from the plausible to the spectacular. One early idea involved a giant swarm of comets, perhaps thousands or even millions of them, stirred up by a passing star and now circling Tabby's star in a chaotic cloud. This could explain the irregularity and the deep dips as clumps of dust and ice passed in front of our view. Others suggested the aftermath of a catastrophic planetary collision, a vast, expanding ring of debris from shattered worlds slowly obscuring the star. More recent studies point to uneven clouds of interstellar dust drifting between us and the star, though this too has problems explaining the specific patterns observed. Then, of course, there is the most famous and provocative hypothesis. In the 1960s, physicist Freeman Dyson speculated that a sufficiently advanced civilization would eventually need to capture the entire energy output of its star. They might construct a vast swarm of orbiting collectors, a so-called Dyson sphere, which would partially block the star's light from our perspective. The irregular, deep dimming of Tabby's star seemed for a moment to fit that speculative profile, sparking headlines around the world about the potential discovery of alien megastructures. Astronomers, while fascinated, have always leaned toward natural explanations as they must. The alien megastructure idea is a hypothesis of last resort, only considered after every conceivable natural phenomenon has been exhausted. And indeed, follow-up observations have provided some clues that point away from solid structures. The star dims slightly more in blue light than in red light, which is characteristic of scattering by fine dust, not the hard edge of a solid object. Yet this does not solve the mystery, it just refines it. We are likely not looking at an alien engineering project, but we are also not looking at anything we have seen before in the cosmos. The exact nature of that colossal, chaotic dust cloud or swarm of fragments, and what event could have possibly created it, remains utterly unknown. Tabby's star stands as a permanent reminder that the universe is capable of architectures and events far stranger than our standard textbooks allow, a single, flickering beacon whose true story we have only begun to read. The flickering enigma of Tabby's star is a mystery of deep shadows, but some of the cosmos's greatest puzzles are written in brilliant, swirling light. At the top of our solar system, crowning the majestic ringed planet Saturn, there is a shape that should not exist. For over 40 Earth years, a perfect, colossal hexagon has been etched into the clouds at Saturn's North Pole, a geometric wonder so precise it looks like the work of some cosmic architect. This is not a trick of perspective or a fleeting storm. It is a permanent atmospheric feature wider than our entire planet, a six-sided jet stream of screaming winds that has endured across decades, perhaps even centuries. The Voyager spacecraft first glimpsed its strange angular shadow in the 1980s, and decades later, NASA Cassini orbiter arrived to stare directly into this swirling abyss, capturing it in breathtaking detail. The hexagon is a wall of cloud, a towering atmospheric wave tracing a razor-sharp border between different bands of Saturn's weather. Inside its boundaries, the planet's north pole is a calm, warm vortex, but the hexagon itself is a highway of winds racing at over 300 miles per hour. How does a chaotic, fluid atmosphere on a planet with no solid surface spontaneously generate and maintain a shape more commonly found in a honeycomb or a crystal? The answer may lie not in alien engineering, but in the fundamental physics of rotating fluids. Here on Earth, scientists have recreated hints of this phenomenon in the lab. When a circular container of liquid is placed on a spinning table and a smaller ring inside it rotates at a different speed, the fluid between them can sometimes organize itself into stable polygons, squares, pentagons, and yes, hexagons. This happens because of shear, the difference in rotational speed between adjacent bands of fluid. Under the right conditions, this shear can generate standing waves that manifest as straight-sided shapes. This laboratory insight suggests the Saturn hexagon is likely a gigantic, stable atmospheric wave, a self-organizing pattern born from the extreme difference in wind speeds at Saturn's polar latitudes. Yet understanding the basic principle is a far cry from explaining the reality. Saturn's atmosphere is not a simple pan of water in a lab. It is a deep, turbulent ocean of hydrogen and helium, thousands of miles thick, under immense pressure and bathed in internal heat. The sheer scale and longevity of the hexagon present computational nightmares. Our most powerful supercomputer simulations can produce temporary polygons, but none have yet recreated a hexagon as stable, as large, or as long-lasting as the one we observe. What specific combination of wind shear, atmospheric density, and planetary rotation locks this pattern in place with such geometric perfection? Why a hexagon and not an octagon or a triangle? The Saturn hexagon is a breathtaking demonstration that nature, under the right conditions, can produce order of startling precision from apparent chaos. It is a natural sculpture carved by invisible forces we are only beginning to comprehend, a six-sided sentinel standing watch over a pole of perpetual twilight, reminding us that even the familiar giants in our celestial backyard still hold profound secrets. Saturn's geometric perfection is a local wonder, but there is a far vaster and more unsettling force at work, one that is pulling our entire galaxy and everything around it on a one-way trip into the unknown. This is the mystery of the Great Attractor, a colossal gravitational anomaly in the depths of intergalactic space that acts like a cosmic drain, drawing thousands of galaxies, including our own Milky Way, toward a single point in the void. For decades, astronomers have mapped the motions of galaxies and found a disturbing consensus: we are not drifting randomly. Our local group of galaxies, along with the immense Virgo cluster and countless others, are all streaming in the same direction at a staggering speed of over 600 kilometers per second. It is as if the entire cosmic neighborhood is sliding down a slope toward a hidden, massive valley. The source of this pull lies about 250 million light-years away, in the direction of the constellations Centaurus and Norma. But there is a profound and frustrating problem. That exact spot in the sky lies directly behind the crowded, dusty heart of our own Milky Way. This region is known to astronomers as the zone of avoidance, where the thick disk of our galaxy's stars, gas, and cosmic dust blocks our optical view almost completely. It is like trying to find a distant mountain range while standing in a dense, blinding fog. For years, the Great Attractor was a ghost, a massive concentration of invisible mass inferred solely by its gravitational tug on everything around it. What could possibly be dense enough to pull thousands of galaxies? The first breakthrough came when astronomers began using radio and X-ray telescopes, wavelengths that can pierce through the galactic dust. They began to map the hidden structures behind the zone of avoidance, revealing not a single monolithic attractor, but an immense tapestry of galaxy clusters and superclusters. The dominant structure we now see is the Laniakea supercluster, a cosmic filament of staggering scale that contains our Milky Way, the Virgo cluster, and hundreds of thousands of other galaxies, all bound together by gravity. Within Laniakea, our motion is largely explained as a flow toward the supercluster's dense core, a region called the Norma cluster, so mystery solved. Not quite. While Laniakea explains most of the pull, detailed studies of galaxy motions reveal a residual flow, an extra velocity that suggests something even bigger and more massive lies beyond it, still pulling us. The original Great Attractor seems to be just one knot in a much larger cosmic web, a local overdensity of mostly dark matter that is itself being pulled by something greater. This is the true, lingering mystery. The Great Attractor is not a destination but a signpost. It points to deeper, larger concentrations of mass in the universe that remain hidden from our direct sight, likely vast agglomerations of dark matter weaving the grandest structures of all. We are caught in a cosmic current, flowing toward shadows we are only beginning to map, reminding us that our place in the universe is not a fixed point, but a constant journey toward an unseen and still unexplained gravity well. That unseen current pulling our galaxy hints at a hidden architecture, but what if the oldest map of the universe itself is pointing directly at us? This brings us to one of the most unsettling and controversial findings in modern cosmology, an anomaly so provocative scientists named it the axis of evil. It is a pattern found not in distant galaxies, but in the very first light of creation, the cosmic microwave background. This faint, cold glow is the leftover radiation from the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. For decades, the CMB has been our most powerful tool for understanding the cosmos's origin. The prevailing cosmological model, based on meticulous measurements, tells us this afterglow should be isotropic, meaning statistically the same in every direction, a uniform tapestry of tiny temperature variations that seeded all future structure. But when scientists began analyzing the data from satellites like WMAP and Planck, they noticed something that sent a chill through the astrophysics community. Certain large-scale features in the CMB, specifically its low-order multipoles called the quadrupole and octupole, were not randomly oriented. Instead, they appeared to be aligned with each other in a way that also seemed curiously linked to our own solar system. Their axis of alignment roughly matches the plane of Earth's orbit around the Sun, and even points toward the vernal equinox. In simpler terms, the universe's oldest baby picture seems to have a faint, ghostly frame that lines up with where we happen to be sitting. This is profoundly troubling for one core philosophical pillar of modern science, the Copernican principle. This principle asserts that we do not occupy a privileged or special place in the universe. The cosmos should not, on the largest scales, care about the orientation of our little planet. Finding an alignment between the universe's first light and our local geometry feels like discovering that the foundation of a skyscraper was poured with a pattern that matches the floor tiles in the janitor's closet on the 42nd floor. It is a coincidence so bizarre it strains credibility. So what could explain the axis of evil? The leading and most hoped-for explanation is some form of local contamination. Perhaps dust in our own Milky Way or an unrecognized foreground emission is imprinting this pattern on the data and fooling us into seeing a cosmic signal. Teams have searched exhaustively for such contamination, but so far, no simple foreground source has been able to fully erase the anomaly. Another possibility is a statistical fluke, a cosmic roll of the dice that just happened to produce a pattern that looks aligned from our vantage point. But as the data from more precise missions has come in, the fluke has not gone away, making this explanation less and less satisfying. The most radical possibility is that our standard model of cosmology is incomplete or even wrong in some fundamental way. Could it be that the universe is not isotropic on the largest scales we can observe? Or does this alignment hint at a pre-Big Bang structure, a fingerprint from something that existed before our universe began? The axis of evil remains an open wound in cosmology, a persistent whisper that perhaps we are not seeing the universe as it truly is, but through a lens subtly warped by our own position in a cosmos far stranger than we have dared to imagine. Our place in the cosmos may feel uncertain, but the history of our own celestial companion is written in stone, and it tells a story that defies our basic understanding of planetary evolution. The mystery of the Moon's ancient magnetic field challenges everything we think we know about how rocky worlds behave. Today, our Moon is a silent, magnetically dead world. Spacecraft measurements confirm it lacks a global magnetic field like Earth's protective bubble. But when Apollo astronauts brought back samples of lunar rock, scientists made a startling discovery locked within their crystalline structures. Certain rocks, particularly those that formed over 3 billion years ago, were permanently magnetized. They contained tiny mineral grains, like little compass needles, that had aligned with a magnetic field as the rock cooled and solidified. The strength of this fossilized magnetism, or paleomagnetism, indicated something extraordinary. The Moon once possessed a magnetic field nearly as strong as Earth's is today. This presents a profound paradox. Planetary magnetic fields are generally thought to be generated by what is called a core dynamo. This requires a molten, electrically conductive core, like a ball of liquid iron, and rapid rotation to churn that liquid and generate a planetary-scale magnetic field through a process similar to a bicycle dynamo. The Moon is small, only about 1% of Earth's mass. According to all standard thermal models, such a small body should have lost its internal heat rapidly after its formation. its core solidifying and any dynamo shutting off within a few 100 million years. Yet the lunar rocks tell us this powerful field persisted for over 1 billion years, perhaps even longer. How could a world with a heart so small keep its magnetic fire burning for so long? One compelling theory points to a catastrophic event in the Moon's youth, a massive impact. The idea is that a colossal collision, long after the Moon's formation, could have delivered a tremendous amount of energy, violently stirring the lunar mantle and reheating the core. This temporary injection of chaos could have reignited a dormant dynamo, giving the Moon a second magnetic wind that lasted for ages. Another line of thinking suggests our standard dynamo model is simply incomplete for smaller bodies. Perhaps the Moon's dynamo was powered not by traditional convection in a purely liquid core, but by a different mechanism like the crystallization of an inner core. As a molten core slowly cools, solid iron can freeze out at its center. This process releases buoyant fluid and latent heat, which can drive fluid motions capable of generating a magnetic field. This process is more efficient and can last longer in a smaller body. There is even a more exotic proposal that the Moon's field was not self-generated at all, but was borrowed. In this scenario, the young Moon orbited much closer to a young, vigorously magnetic Earth. The Moon might have been immersed in Earth's extended magnetosphere, effectively magnetizing its surface rocks from the outside in. Yet each of these theories faces significant hurdles. The impact model requires a very specific, very late, and very large collision for which we have little other evidence. The core crystallization model depends on precise and poorly understood details of the lunar core's composition, and the borrowed field idea struggles to explain the strength and longevity of the magnetization seen in rocks from different eras. The silent, gray face of the Moon now seems to guard a secret of a far more dynamic and electrically alive past. It forces us to question whether we truly understand the inner lives of rocky worlds, or if the quiet companions in our night sky once hummed with invisible forces whose origins we have yet to decipher. The Moon's lost magnetic heart is a puzzle locked in ancient rock, but in 2017, a messenger from the void between stars arrived without any history at all. This was Oumuamua, the first confirmed interstellar object ever detected passing through our solar system, and it defied every expectation. The Pan-STARRS telescope in Hawaii spotted it as a faint point of light already on its way out, moving so fast it could only have originated from another star system. Immediately, astronomers scrambled to observe it before it vanished forever into the dark. What they learned in those frantic weeks was a cascade of surprises. First was its shape. By analyzing how its brightness changed dramatically as it tumbled end over end, scientists deduced it was not round. Oumuamua was profoundly elongated, perhaps 10 times longer than it was wide, resembling a cosmic cigar or a flattened pancake. No asteroid or comet in our solar system has such an extreme proportions. Second, as it streaked past the Sun, it showed no visible coma, the fuzzy cloud of gas and dust that surrounds a typical comet. This suggested it was a dry, rocky asteroid, but then came the third and most baffling clue, its acceleration. As Oumuamua swung around the Sun and began its journey back out into interstellar space, its speed did not follow a perfect gravitational trajectory. It was speeding up slightly, as if being gently pushed by an unseen force. For comets, this non-gravitational acceleration is common, caused by outgassing, when sunlight heats icy surfaces and jets of vapor act like tiny rocket thrusters. But Oumuamua showed no coma, no dust tail, no visible signs of outgassing whatsoever. So what was pushing it? The search for a natural explanation has produced intriguing, though still unproven, ideas. One leading theory suggests Oumuamua could be a chunk of molecular hydrogen ice. Hydrogen is the most common element in the universe, but it is notoriously difficult to see in space. A block of solid hydrogen warmed by the Sun would sublimate directly into an invisible gas, providing the thrust for the acceleration without producing any detectable dust or visible coma. The problem is, such hydrogen icebergs are purely theoretical. They have never been observed, and it is unclear if the conditions exist to form them in the vastness of interstellar space. Another idea posits that Oumuamua is a fragment from a Pluto-like world in another star system, a shard of nitrogen ice sheared off by some cataclysm. As the nitrogen sublimated in sunlight, it could have both shaped the object into its strange form and provided the stealthy thrust. This, too, is speculative. Then there is the more provocative hypothesis put forward by Harvard astronomer Avi Loeb. He noted that the acceleration was remarkably smooth, not the jerky, unpredictable thrust you would expect from uneven outgassing. He suggested the possibility, however slim, that Oumuamua could be a piece of alien technology, specifically a light sail. A light sail is a thin, reflective sheet that uses the pressure of sunlight itself for propulsion, much like a boat sail uses wind. Its elongated shape would be ideal for such a structure, and the smooth solar radiation pressure could explain the acceleration. Loeb argued we should at least consider the possibility as scientists and not dismiss it out of hand. The astronomical community largely remains skeptical of the artificial origin idea, emphasizing that extraordinary claims require extraordinary evidence, and a natural explanation is still more likely. Yet the core of the mystery remains. By the time we noticed Oumuamua, it was already leaving. We had only a few weeks of blurry, distant observations of a tiny, faint speck. We never saw it clearly, never resolved its shape with a telescope, never analyzed its composition with a spectrometer. It is now forever beyond our reach, receding into the interstellar deep. Oumuamua, whose name means scout or messenger from the distant past in Hawaiian, lived up to its name. It delivered a single, cryptic message that the space between stars is not empty, but filled with travelers of unknown form and origin. It is a symbol of our profound ignorance, a fleeting glimpse of a reality far stranger than our solar system had prepared us for, a silent envoy that passed through our neighborhood, whispered a riddle, and disappeared before we could ask a single question. Oumuamua's silent passage reminds us how much lies unseen between the stars, but at the very heart of our own galaxy, a different kind of invisible signal is shouting for attention. For over a decade, the Fermi Gamma-Ray Space Telescope has been mapping the high-energy sky, and its data revealed a profound and puzzling glow. Concentrated at the core of the Milky Way is a massive spherical excess of gamma-ray radiation, a diffuse haze of the most energetic light in the universe that our existing catalog of cosmic objects cannot explain. Gamma rays are the signature of the most violent events in nature, produced by supernova remnants, pulsars, and the furious jets of black holes. Astronomers naturally expected to see some gamma rays from the crowded galactic center, but the Fermi data showed far more than the sum of all known sources could account for. This surplus forms a smooth, symmetrical fog extending thousands of light years from the core, a shape that is strangely difficult to produce with the usual suspects. Known gamma-ray sources like pulsars tend to be point-like and clustered, not smoothly distributed in a perfect sphere. So what is generating this pervasive, high-energy hum at the galaxy's core? The most tantalizing possibility involves the greatest cosmic ghost of all, dark matter. According to this theory, the center of our galaxy is not just packed with stars, but also with an incredibly dense concentration of dark matter particles. If these particles are their own antimatter opposites, as some models suggest, they could annihilate upon collision, converting their mass directly into energy and producing a spray of gamma rays. The smooth, spherical shape of the excess matches what many dark matter models predict, as the invisible particles would form a vast, round halo. Discovering that this glow is indeed from dark matter annihilation would be a monumental breakthrough, the first direct detection of the elusive substance that shapes the cosmos. It would open a window into particle physics far beyond what any Earth-bound collider could achieve. Yet extraordinary claims demand extraordinary evidence, and the dark matter explanation is fiercely debated. The leading alternative is far more conventional but no less fascinating. It suggests the glow comes from a vast, hidden population of ancient, spinning stellar corpses called millisecond pulsars. These are neutron stars that have been spun up to incredible speeds by siphoning material from a companion star, and they beam out powerful gamma radiation. Thousands of these faint, point-like objects, each individually too dim for Fermi to resolve, could together create the illusion of a smooth, spherical glow. Finding even a few of these pulsars in the region would lend strong support to this idea. Another theory points to the sleeping giant at the very center, the supermassive black hole Sagittarius A star. While it is quiet now, it may have been explosively active in the relatively recent past, perhaps a few million years ago. A past outburst or jet from the black hole could have flooded the central region with high-energy particles that are still slamming into gas clouds and producing gamma rays today. Each explanation paints a dramatically different picture of our galactic heart. Is it a laboratory for the fundamental physics of dark matter, a graveyard of countless unseen stellar remnants, or the fading echo of a black hole's ancient fury? The debate continues, with scientists meticulously analyzing every new sliver of data, searching for the telltale clumpiness that would point to pulsars, or the specific energy signature that would scream dark matter. The galactic center excess is a beacon of unanswered questions, a mysterious light at the end of our cosmic street whose true source remains just out of sight, challenging us to look deeper into the darkness we thought we knew. The mysterious glow at our galaxy's heart speaks of invisible forces, but sometimes the cosmos offers a spectacle of structure so perfect it looks designed. Far from the crowded center, about 2,300 light-years away in the constellation Monoceros, a dying star has painted a masterpiece of geometry against the dark. This is the red rectangle nebula, a celestial object that earns its name with stunning, almost artificial clarity. Through the lens of the Hubble Space Telescope, it appears not as a typical, chaotic cloud, but as a vivid, nested series of rectangular rungs, like a cosmic ladder or a set of glowing boxes stacked within one another. At its heart, two bright spikes form a sharp X shape, the signature of a powerful, opposing outflow. This is not the spherical shroud of a typical planetary nebula, nor the simple hourglass of a bipolar one. It is a structure of startling angular precision, a testament to the fact that stellar death can be an art form of breathtaking order. The central engine is a binary star system known as HD 44179. One of these stars is a post-asymptotic giant branch star, a luminous giant in its final act, furiously ejecting its outer layers into space. Its companion star orbits closely, and their intricate gravitational dance is the key to the sculpture. As the dying primary star blows out a thick, slow wind of gas and dust, the smaller companion star orbits within this cloud, carving out a cavity and funneling material into two opposing cones or jets. Furthermore, astronomers believe a dense, donut-shaped ring of dust called a torus girdles the binary pair at its equator. This torus acts like a stencil, constricting the outward flow of material. The star's wind can only easily escape out the poles, above and below the dust ring, creating the two opposing cones we see as the X-shaped spikes. But here lies the enduring mystery. How does this interplay of wind, orbit, and dust produce such razor-sharp 90-degree corners? The smooth, concentric rectangular rungs are even more puzzling. One leading explanation involves episodic outbursts from the dying star. Imagine it does not shed its skin at a steady rate, but in a series of pulses or hiccups. Each major pulse of material expands outward until it slams into the slower-moving wind from the previous pulse, creating a standing shock wave. This shock compresses the gas and dust, making it glow brightly and trace a sharp edge. Because the entire system is constrained by that central dust torus, these shock fronts take on a boxy, rectangular form as they expand. The result is a set of glowing, nested rectangles, a fossil record of the star's final rhythmic gasps. While this model is elegant, it remains a work in progress. The precise physics that allows for such clean, geometric shock fronts, repeated over and over with such symmetry, is incredibly difficult to simulate. It requires a perfect, delicate balance of mass loss rates, wind speeds, and binary orbital dynamics. The red rectangle is a natural laboratory for studying how structure emerges from chaos, a demonstration that under the right conditions, the laws of physics can produce art that rivals the most precise human engineering. It stands as a beautiful, haunting reminder that even in death, stars can obey a hidden geometry, leaving behind a luminous, angular ghost that challenges our understanding of form itself in the vast and winding paths of stellar evolution. The geometric perfection of the red rectangle is a cosmic artwork from a dying star, but the very first strokes on the universe's canvas contain a fundamental error in their chemical signature. This is the lithium problem, and it begins in the furnace of creation itself. In the first 20 minutes after the Big Bang, the universe was a seething, dense soup of particles cooling rapidly from an unimaginable heat. During this brief, explosive window, known as Big Bang nucleosynthesis, the first atomic nuclei fused together, primarily hydrogen and helium, but also trace amounts of two heavier elements, deuterium and lithium. The precise amounts produced are not guesswork. They are a precise prediction based on our well-tested understanding of nuclear physics and the measured density of the universe. For deuterium, the predictions match the observations in ancient gas clouds beautifully. For helium-4, the agreement is also excellent, but for the third lightest element, lithium-7, the numbers are catastrophically wrong. Our best models of the Big Bang's nuclear cooking predict that the oldest stars in our galaxy, which formed from nearly pristine gas, should have about 3 times more lithium in their atmospheres than we consistently measure. It is not a small discrepancy, it is a factor of 3, a glaring mismatch between our theory of the universe's birth and the fossil evidence written in starlight. This is not about lithium in general. Modern stars like our Sun have processed and created lithium over time. The problem is specifically with the primordial lithium, the amount that was forged in that first cosmic fire and should be preserved like a time capsule in the atmospheres of the most ancient metal-poor stars. Astronomers have searched for decades, and the answer is always the same: the lithium is missing. Where did it go? One line of investigation looks for new physics in the infant universe. Could there have been unknown particles or forces at play during nucleosynthesis that altered the nuclear reaction rates, perhaps destroying lithium as quickly as it formed? Some theories invoke exotic ideas like decaying dark matter particles that could have injected energy and broken apart lithium nuclei. While intriguing, these solutions often feel like inventing a new cosmic entity just to solve one specific number, and they must not upset the perfect agreement we have for deuterium and helium. A second, more conservative possibility points to the stars themselves. Perhaps our understanding of stellar interiors is incomplete. Could these ancient stars, over their billions of years of life, have somehow dragged surface lithium down into their hot cores where it was destroyed? This process, called diffusion or rotational mixing, is plausible, but detailed models struggle to make it efficient enough to deplete the lithium by the exact factor of 3 across so many different stars. A third, fascinating idea suggests we might be misreading the stars entirely. What if the oldest stars we are measuring are not pristine? What if they already ingested planets early in their lives? A rocky planet falling into a star would dilute its surface lithium, because planets like Earth are lithium-poor compared to the primordial cosmic mix. It is a cosmic detective story with high stakes because the lithium problem is not just about one element. It is a direct test of our understanding of the universe's first moments. If our models of Big Bang nucleosynthesis are off by a factor of 3 for lithium, what else might we be missing about that primordial epoch? It is a quiet but persistent crack in the foundation of cosmology, a reminder that the recipe for the universe, written in the language of nuclear physics, might still have one ingredient we have not yet learned to read. While the lithium problem questions the universe's first chemical recipe, other cosmic messengers arrive with energies that defy the very laws of their journey. These are ultra-high energy cosmic rays, and they are not rays of light but subatomic bullets, usually single protons, screaming into our atmosphere. Their power is almost incomprehensible. Each one carries the kinetic energy of a professionally thrown baseball, but compressed into a particle 1,000,000 billion times smaller. To put it in laboratory terms, the most energetic of these cosmic rays hit with millions of times more force than anything we can create in our most powerful particle accelerators, like the Large Hadron Collider. They are the universe's ultimate natural particle accelerators, and we have no idea how they work. The mystery deepens with a fundamental cosmic roadblock known as the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. The universe is not empty, it is filled with the faint, cold afterglow of the Big Bang, the cosmic microwave background radiation. For a proton traveling near the speed of light across millions of light years, this radiation is not a harmless glow, it is a thick fog. When an ultra-high energy proton slams into a photon from this background radiation, the collision is so violent it can create new particles, sapping the proton's energy. According to our best calculations, this means a proton with the energies we detect should not be able to travel more than about 150 million light-years before it loses its punch. Its source must be in our cosmic backyard, and that is the heart of the puzzle. We have caught these unimaginably powerful particles, and we know they cannot have come from very far away. But when we look around within that 150 million light-year radius, we see nothing obvious that could possibly be their gun. What cosmic engine can take a single, tiny proton and fling it across space with such ferocious energy? The usual suspects fall short. Supernova remnants, the powerful shockwaves from exploding stars, are impressive, but they cannot reach these extreme energies. Even the turbulent centers of normal galaxies seem insufficient. Scientists have two leading but problematic candidates. The first are active galactic nuclei, the monstrous cores of galaxies where supermassive black holes devour matter and blast out jets of plasma moving at nearly the speed of light. Perhaps magnetic fields in these relativistic jets could act as a natural synchrotron, accelerating particles to these ultra-high energies. The second candidate is even more violent: gamma-ray bursts, the most energetic explosions since the Big Bang, which could theoretically create a similar shockwave in their aftermath. The problem is one of geography and frequency. While we do have a few active galaxies within range, like Centaurus A, their jets are not always pointed at us, and the cosmic rays we detect seem to come from all directions, not just from these known powerhouses. As for gamma-ray bursts, they are incredibly rare events in any given galaxy, making it statistically difficult to explain the steady, if sparse, rain of these particles we detect. So we are left with a profound disconnect. We have the bullets, we know they were fired from a nearby neighborhood, but when we search the houses, we cannot find a cannon large enough to have shot them. It suggests that within the relatively quiet galactic suburbs around us, there may be transient, catastrophic events we have not yet learned to see, or that our understanding of particle acceleration in extreme environments is fundamentally incomplete. Each time one of these rare particles tears through our atmosphere, it is a message from a hidden cosmic powerhouse, a signature of violence on a scale we can detect but cannot yet locate, reminding us that the universe is still capable of throwing punches we do not know how to throw back. These cosmic bullets are messengers from hidden accelerators, but a stark and silent edge in our own solar backyard whispers of a different kind of missing piece. Far beyond the orbit of Neptune, in the cold, dark realm of the Kuiper Belt, astronomers expected to find a gently fading frontier. This vast disk of icy leftovers from the solar system's formation should, according to every standard model, contain a smoothly increasing number of objects out to a certain distance, like a cosmic gravel pile that gets gradually thicker toward its outer rim. Instead, our surveys have revealed something startling: a sudden cliff. The population of these frozen worlds does not taper off, it plummets. At roughly 50 astronomical units from the Sun, about 50 times the Earth-Sun distance, the density of detectable Kuiper Belt objects drops off a precipice. It is as if someone built a fence at the edge of the solar system's construction site and told the builders to stop scattering debris beyond it. This Kuiper Belt cliff is one of the cleanest and most puzzling features in our planetary neighborhood, a stark boundary where our expectations crash into an unexplained void. So what could have carved such a sharp edge in this distant debris field? One of the most compelling theories points to the gravitational hand of a hidden architect, the hypothetical planet 9. This proposed world, perhaps 5 to 10 times the mass of Earth, is thought to orbit far beyond the cliff in a stretched elliptical path. The gravitational influence of such a massive object could act as a cosmic shepherd, clearing out and reshaping the orbits of smaller bodies in the inner Kuiper Belt, potentially sculpting that abrupt outer edge. In this scenario, the cliff is not a natural end to the primordial disk, but a scar carved by the distant wanderings of an unseen giant. Another line of thinking looks not outward for an answer, but backward in time. Perhaps the cliff is a fossil, a preserved edge from the solar system's violent infancy. Our current models suggest the young sun was born in a crowded stellar nursery, surrounded by sibling stars. The gravitational tides from a passing star in that early chaos could have stripped away the outer portion of the protoplanetary disk, shearing it off and leaving the sharp boundary we see today. Alternatively, the disk itself may have had a natural edge, perhaps where the temperature in the primordial cloud dropped so low that ices could not condense efficiently, creating a natural cutoff in the building blocks for larger objects. Each explanation paints a dramatically different picture of our system's history. Is the Kuiper Belt cliff a signpost pointing to a major, undiscovered planet still lurking in the perpetual twilight? Or is it the ghost of a stellar encounter from 4.5 billion years ago, a permanent mark left by a sibling star that has long since drifted away into the galactic night? This quiet edge in the darkness is more than an empty space. It is a question etched into the frozen architecture of our solar system, a clue waiting to be read about the forces, both seen and unseen, that truly built our celestial home. That sharp edge in our own solar system's construction zone feels like a silent monument to the past, but on the rust-red plains of Mars, a different kind of clue flickers in and out of existence, a ghostly breath that could rewrite history. The mystery of Martian methane is a detective story written in parts per billion, a tantalizing whisper of gas that appears, lingers, and then vanishes against all expectations. Our robotic emissaries, from orbiters like the European Space Agency's Mars Express to NASA, a Curiosity rover trundling inside Gale Crater, have all sniffed the thin Martian air and reported the same baffling signal: sporadic spikes of methane gas. On Earth, methane is a potent signature. While it can be produced by purely geological reactions, like when water interacts with certain rocks in a process called serpentinization, the vast majority of our atmospheric methane is biological, belched by microbes in wetlands, emitted by livestock, and leaked from fossil fuel deposits. Finding it on another world immediately raises the electrifying question: is it a sign of geology or of life? The puzzle deepens with the gas's bizarre behavior. Curiosity's instruments have shown that background methane levels are vanishingly low, almost zero. but on several occasions the rover has measured sudden, dramatic plumes where methane concentrations spike by a factor of 10, only to dissipate back to baseline within a matter of weeks. This fleeting nature is the first major enigma. Mars has sunlight that breaks down methane, but standard photochemical models suggest the gas should linger in the atmosphere for several hundred years before being destroyed. The fact that it clears so rapidly points to an unknown, highly efficient destruction mechanism at work right now on the Martian surface or in its lower atmosphere. Some scientists speculate that reactive chemicals like perchlorates in the Martian soil could be rapidly scrubbing the gas from the air, a process we do not see on Earth. Then there is the mystery of the source. The plumes are localized, not globally mixed, suggesting the methane is leaking out from specific, isolated spots. What is creating these sporadic belches? A purely geological source is plausible. Liquid water interacting with the mineral olivine deep underground can produce methane through serpentinization. Perhaps Mars has hidden, active hydrothermal systems where this chemistry is ongoing, occasionally venting gas to the surface through cracks and fissures. Yet no definitive evidence for such widespread, active geology has been found. The other possibility, the one that quickens the pulse, is a biological one. Could there be reservoirs of methanogenic microbes living in aquifers deep beneath the frozen Martian soil, protected from radiation, metabolizing hydrogen and carbon dioxide and producing methane as a waste product? These organisms exist in extreme environments on Earth, deep in mines or under ice sheets, and Mars could offer similar niches. The quest for an answer is now a central focus of Mars science. NASA Perseverance rover, while not carrying a methane sniffer itself, is caching samples that may one day be returned to Earth for analysis, potentially holding mineral clues to past or present processes. The ExoMars Trace Gas Orbiter, a European and Russian mission designed specifically to solve this mystery, has added its own confusing data point, detecting no methane in the global atmosphere at its orbital altitude, even as Curiosity measured a spike from the ground. This suggests the gas is destroyed or confined very close to the surface, making the mystery even more acute and localized. Is Mars quietly breathing? Each sporadic detection is like catching a single word from a conversation happening deep underground, a conversation we cannot yet hear in full, leaving us to wonder if we are listening to the slow grind of rocks or the faint, metabolic murmur of something truly alien. The ghostly methane on Mars speaks of chemistry we can almost grasp, but scattered across the galaxy is a spectral signature from molecules we cannot name. In the faint infrared glow of nebulae and star-forming clouds, astronomers detect a series of mysterious spikes and bands, a barcode of light that does not correspond to any single atom or simple gas. These are the unidentified infrared bands, and they are among the most common yet enigmatic features in the cosmos. Wherever there is gas and dust being lit up by young, hot stars, these bands appear, a persistent hum of complex chemistry happening in the void. They are not the sharp lines of neon or hydrogen, but broader, more blended features, the fingerprint of something much larger and more intricate. For decades, the prime suspect has been a family of molecules known as polycyclic aromatic hydrocarbons, or PAHs. Imagine the soot from a candle flame, not the black particulate, but the complex ring-shaped molecules that form within it. PAHs are flat, stable structures made of carbon and hydrogen, like tiny hexagonal tiles fused together into sheets. They are tough, can survive harsh radiation, and vibrate in very specific ways when bathed in starlight, emitting infrared light at characteristic wavelengths. The problem is, while the observed bands look very much like what we would expect from PAHs, they do not match perfectly. Laboratory measurements of individual PAH molecules never quite reproduce the exact pattern seen in space. The cosmic bands are smoother, broader, as if we are not hearing a single clear note from one type of molecule, but a blended chord from an entire orchestra of them, all playing similar but slightly different tunes. This suggests the interstellar medium is not filled with one specific pH, but with a vast, diverse population of these large organic molecules, each with slightly different structures, sizes, and attached chemical groups. Some might be charged, others neutral, some small, others large. Their combined emission creates the familiar but fuzzy bands we see. The profound implication is that complex organic chemistry is not a rare event, it is a universal process. These unidentified bands are seen in our own galaxy, in nearby galaxies, and in light that has traveled for billions of years. They are the smoke from cosmic fires that forge the building blocks of complexity. PAHs are thought to be key stepping stones on the path from simple atoms to the more complex molecules that could eventually lead to life. They could have been delivered to the early Earth by comets and meteorites, seeding our planet with organic material. Yet their anonymity is a constant frustration. We see their collective shadow everywhere, but we cannot point to a single, definitive molecule and say that is the culprit. It is like knowing a vast, influential family is at work shaping the world, but never being able to meet any of its individual members. The unidentified infrared bands are a fundamental mystery in astrochemistry, a reminder that the space between stars is not empty, but a vast, diffuse chemical laboratory where the recipes for complexity are being written in a language we are still struggling to translate. That faint chemical signature in deep space speaks of universal building blocks, but our own planet's earliest chapters contain a glaring contradiction in its very climate. Billions of years ago, our Sun was a weaker star. According to our best models of stellar evolution, the young Sun shone with only about 70% of the brightness it has today. That difference is not trivial. It is the difference between a warm summer day and a perpetual global ice age. Under that faint young sun, Earth's oceans should have been frozen solid for its first 2 billion years, a glittering snowball locked in ice from pole to pole. Yet, when we read the geological record, the oldest rocks on Earth tell a completely different story. We find sedimentary rocks that formed in liquid water over 3.8 billion years ago. We find fossilized microbial mats called stromatolites dating back 3.5 billion years, clear evidence that life not only existed but was already thriving in warm, shallow seas. This is the faint young sun paradox, a cosmic riddle written in stone and starlight, forcing us to ask how a planet could stay warm under a cooler sun. The most widely accepted solution lies in the planet's ancient air. Today, we worry about too much carbon dioxide warming our world, but back then, Earth may have needed a much thicker blanket. A far denser atmosphere, rich in potent greenhouse gases like carbon dioxide and methane, could have trapped enough of the sun's weaker heat to keep the global thermostat above freezing. Think of it as turning up the planetary heat while the cosmic furnace was still warming up. Methane, in particular, is a powerful greenhouse gas, and some models suggest that early microbial life itself, those same organisms that left fossils, could have been producing it in vast quantities, creating a self-sustaining biological thermostat. But the puzzle is more complex than just adding more gas. Other factors likely played crucial roles. The early Earth spun faster, with days that were only a few hours long, which could have altered cloud formation and weather patterns in ways that retained more heat. The continents were also arranged differently, and the planet's reflectivity or albedo was lower, with less icy surface area and perhaps darker volcanic landmasses that absorbed more sunlight rather than bouncing it back into space. Some even speculate that the sun itself might have been more active in its youth, with stronger solar winds or more frequent flares that could have interacted with Earth's primitive magnetic field and atmosphere in warming ways we do not fully understand. While the greenhouse gas explanation is the leading theory, making all the pieces fit is an ongoing challenge for climate scientists and planetary geologists. They must balance the faint sunlight with just the right atmospheric cocktail to create a stable, habitable climate for hundreds of millions of years, all while matching the precise chemical signatures locked in those ancient rocks. It is a delicate act of cosmic detective work, reconstructing the air of a world that vanished eons ago. The faint young sun paradox is more than a climate puzzle. It is a testament to Earth's remarkable resilience and a crucial guide in our search for life elsewhere. If a planet can find a way to stay warm against the odds, what other ingenious climatic balancing acts might be possible on distant worlds orbiting their own faint young stars? Earth's ancient climate paradox reveals a world-finding balance, but some celestial structures achieve a balance so perfect it seems impossible. Suspended in the void like a cosmic bull's-eye is Hoag's object, a galaxy that defies every expectation of how such systems form. Through a telescope, it presents an image of breathtaking, serene symmetry. At its heart sits a nearly perfect sphere of aging, yellowish stars, a dense and tranquil core. Encircling it at a vast and empty remove is a flawless ring of brilliant blue, a younger population of hot, massive stars tracing a luminous circle against the black. Between them lies a profound and seemingly empty gap, a dark moat of space that cleanly separates the two stellar populations. It looks less like a galaxy born of chaos and more like a piece of celestial art, a cosmic mandala painted with stars. This serene beauty, however, masks a formation history that has frustrated astronomers for decades. The most common way we see ring structures in galaxies is through a violent collision. When a smaller galaxy plunges through the disk of a larger spiral galaxy, the gravitational shockwave can trigger a wave of star formation that propagates outward, creating a temporary, messy ring of new blue stars. But Hoag's object shows no signs of such a violent past. There is no remnant of a disrupting galaxy at its center, no tidal tails of stars flung into space, no distortion in its perfectly round core. It is isolated, pristine, and undisturbed, a picture of cosmic peace that rules out the standard collision scenario. The leading alternative theory is intricate and speculative. It suggests that billions of years ago, Hoag's object might have been a barred spiral galaxy, one with a central bar of stars. In this model, instabilities within that bar could have caused it to dissolve over immense timescales, its stars migrating inward to form the dense core we see today. Meanwhile, gravitational perturbations could have funneled gas outward into a vast, unstable ring, which then collapsed to form the brilliant blue circle of young stars. It is an elegant idea, but it is not fully satisfactory. The process is extraordinarily delicate, requiring a specific and fragile sequence of events to leave such a clean gap and such a perfectly symmetrical ring. Why did all the star formation happen only in that precise, detached ring, and not in the gap or the core? Why is the ring so perfectly circular, and why is the core so perfectly round? No simulation has yet recreated Hoag's object in all its idealized glory, starting from a typical barred spiral and ending with this flawless target. It stands alone, a cosmic oddity of such geometric purity that it challenges our narratives of galactic evolution. We are left to wonder if it is the rare survivor of a vanishingly unlikely process, or if it represents a pathway to structure we have not yet dared to imagine, a silent, spinning riddle where beauty and mystery are one and the same. The serene geometry of Hoag's object speaks to the hidden order within chaos, but for every cosmic rule we think we have uncovered, the universe provides a glaring exception. This brings us to a profound and recent challenge to one of astronomy's most fundamental ideas, the dark matter paradigm. While the gravitational pull of unseen mass perfectly explains why spiral galaxies spin too fast, a handful of bizarre, ghostly galaxies are spinning as if there is nothing there at all. These are the dark matter-deficient galaxies, and their existence is shaking the very foundation of how we think galaxies are built. The story centers on two ethereal smudges of light, NGC 1052 and DF4, discovered in a survey of the sleepy constellation Cetus. They are classified as ultra-diffuse galaxies, enormous in size but so sparse in stars they are nearly transparent, like cosmic jellyfish. Astronomers, expecting these faint giants to be dominated by dark matter like every other galaxy of their scale, set out to measure their mass. They used two independent methods, first by clocking the motion of 10 bright star clusters orbiting within each galaxy, and second by tallying the total starlight and estimating how much normal matter that represented. The results were staggering. The motions of the star clusters were slow and sedate, indicating the total gravitational mass of each galaxy was almost exactly equal to the mass of the stars themselves. There was no room left for dark matter. According to these measurements, these galaxies are made of stuff we can see. This is the opposite of the rotation curve anomaly that dark matter was invented to solve. It is as if you found a car that could drive 100 miles on a single thimble of gasoline, defying every law of physics, and then found another car next to it that needed 1,000 gallons just to start its engine. The immediate question is, how is this even possible? If dark matter is the invisible scaffold upon which all galaxies form, how did these structures build themselves without it? One compelling, if violent, explanation is cosmic robbery. Imagine DF2 and DF4 were once normal dwarf galaxies, complete with their own halos of dark matter, that ventured too close to a monstrous neighbor, the giant elliptical galaxy NGC 1052. The immense gravitational tides from this Goliath could have ripped away their dark matter, stripping it into the intergalactic void while leaving the more tightly bound stars relatively intact. It is a form of extreme tidal stripping, leaving behind ghostly stellar skeletons. Supporting this idea, both galaxies are indeed located near this massive elliptical, and they show other signs of a traumatic past. However, the puzzle deepens because recent, more precise measurements have sparked a fierce debate. Some teams, using different methods or reanalyzing the same data, argue that the star clusters might not be true tracers of the galaxy's gravity, or that the distances to these galaxies were miscalculated, which would throw off all the mass estimates. The controversy is intense because the stakes could not be higher. If these galaxies are confirmed to be truly devoid of dark matter, it is a double-edged sword for science. On one hand, it would be a stunning blow to theories that try to replace dark matter with a modification to Newton's laws of gravity, known as MOND. These modified gravity theories predict that the anomaly in rotation curves should be universal, affecting all galaxies in the same way. Finding galaxies that perfectly obey Newton's laws without any dark matter would severely undermine that entire approach. On the other hand, it creates a headache for standard dark matter theory, which must now explain how such objects could form in a universe where dark matter is supposed to be the primary ingredient. It forces us to consider a more complex and messy picture of galaxy formation, one where interactions and sheer luck play a larger role than we thought. These faint, puzzling galaxies are more than just cosmic outliers. They are critical stress tests for our most fundamental theories of the cosmos, proving that even our best explanations must remain humble before the evidence. While dark matter-deficient galaxies test the rules of cosmic construction, the radio sky itself has begun to reveal structures of such bizarre scale they were hiding in plain sight. These are the odd radio circles, or ORCS, and they are exactly what their name suggests: enormous, faint, perfect circles that only appear in radio wavelengths, scattered across the cosmos like ghostly celestial smoke rings. They were not discovered by a lone astronomer peering through an eyepiece, but by the vast, automated eyes of modern sky surveys like ASCAP in Australia, which maps the universe in radio light with unprecedented speed and sensitivity. The computers flagged them simply because they looked wrong, perfect circles where nature usually makes blobs, jets, or spirals. Each ORC is colossal, so large it could easily swallow an entire galaxy, with diameters spanning hundreds of thousands of light-years. Yet, when astronomers point every other kind of telescope at their locations, searching in optical, infrared, or X-ray light, they find nothing. It is as if someone drew a circle on the sky with invisible ink that only one special camera can see. The circles are empty, or more accurately, they are filled with something that only radio waves can reveal. So what are these faint, gargantuan rings? The hunt for an explanation is wide open, with each leading theory pushing the limits of known physics. One idea suggests we are looking at the aftermath of a truly titanic explosion. Perhaps two supermassive black holes, each at the heart of a galaxy, finally spiraled together and merged, sending a monstrous shockwave of energy blasting out in all directions. This shockwave, propagating for hundreds of millions of years, could have swept up and energized electrons, creating a spherical shell that glows in radio waves as we see it edge on, making it look like a circle. Another possibility points to a phenomenon called a starburst termination shock. Imagine a galaxy going through an extreme, violent burst of star formation. The combined winds from millions of exploding stars and newborn stellar giants could blow a galactic-scale bubble into the surrounding intergalactic gas. The outer edge of that bubble, where the galactic wind slams to a stop, could form a sharp, spherical shock front that radiates in radio waves. There is an even more exotic proposal that we are looking down the barrel of a jet from an active galactic nucleus. The supermassive black hole at a galaxy's core can sometimes fire out relativistic jets of particles for millions of light years. If one of those jets is pointing almost directly at us, the base of the jet might appear as a bright central spot, while the wider lobe where the jet impacts surrounding material could be projected on the sky as a faint circular ring. Yet, for each of these ideas there is a catch. The merger shockwave should have other signatures, like gravitational waves or high-energy radiation, that we do not see. The starburst galaxy should be brilliantly visible in other wavelengths at the circle's center, and often it is not. The jet hypothesis requires a very specific and unlikely alignment for multiple, independent circles scattered across the sky. The most intriguing possibility is that ORCs represent a completely new class of astronomical object, a phenomenon we have never before imagined because we never had the right tools to see it. Their recent discovery is a humbling and thrilling reminder. We have mapped the stars for millennia, but the invisible radio universe is a frontier we are only now exploring in detail, and it is already showing us that the cosmos still has grand, mysterious architectures waiting to be understood, drawn in light we cannot see with our eyes on a scale that dwarfs our own galaxy. These ghostly circles drawn in radio light remind us how much of the cosmos remains unseen, but perhaps the most personal mystery of all involves the very stuff we are made of. You, the planets, the stars, every atom in every galaxy we can see, all of this is what scientists call baryonic matter, the ordinary protons and neutrons that form the bedrock of our physical reality. For decades, cosmologists have tallied a budget for the universe, a ledger of all its contents based on the exquisite measurements of the cosmic microwave background. This ledger tells us precisely how much ordinary matter should exist. Yet when astronomers add up everything they can actually see, all the stars, galaxies, glowing gas clouds, and dust, the numbers come up shockingly short. Nearly half of all the ordinary matter in the universe is simply missing. This is the missing baryon problem, and it is a humbling realization that we cannot even account for the familiar atoms that constitute our own existence. The discrepancy is not small. Observations of the ancient light from the Big Bang tell us that baryons should make up about 5% of the total cosmic energy budget. But our most comprehensive inventories of the nearby universe, the one we can observe with our best telescopes, only find about half of that predicted amount. So where did the rest of the atoms go? They did not vanish into dark matter or dark energy. Those are separate, exotic components. These are the same protons and neutrons found in your body. They have just been hiding in plain sight. The leading theory points to the vast, empty stretches between galaxies. This space is not truly empty. It is threaded by the cosmic web, a filamentary structure of dark matter along which galaxies are strung like pearls on a necklace. Scientists believe the missing baryons are there in the form of an incredibly diffuse, superheated plasma known as the warm-hot intergalactic medium, or the WHIM. Imagine the gentlest, most tenuous fog imaginable, but one so hot it glows in X-rays with temperatures ranging from 100,000 to 10 million degrees. This gas is so thin that a cube of space the size of your average bedroom might contain only a single atom. Trying to detect it is like trying to see a single, faint light bulb from thousands of miles away through a dense, perpetual haze. It emits almost no light of its own, and it is too hot and spread out to cast a clear shadow on more distant light sources. For years, it existed only in theory, the perfect hiding place for the universe's lost atoms. The breakthrough in hunting the WHIM has come from using the universe itself as a tool. Astronomers now look at the brilliant X-ray light from distant quasars, the luminous cores of active galaxies. As that light travels across billions of light years to reach us, it passes through these filaments of hot gas. Specific atoms within the WHIM, like highly ionized oxygen, can absorb very particular wavelengths of that background X-ray light. By analyzing the quasar's spectrum, scientists can search for the faint, telltale dips that signal the presence of these absorbing atoms along the line of sight. It is like finding the silhouette of a nearly invisible ghost by watching how it dims a distant, brilliant searchlight. Recent observations using X-ray telescopes like XMM Newton and Chandra have begun to find these fingerprints. They have detected the absorption lines from oxygen atoms in the predicted locations, tracing the outlines of the cosmic web's filaments. This is strong evidence that the missing baryons are indeed there, woven into the grand architecture of the universe in the form of this hot intergalactic fog. The hunt is now on to map this hidden reservoir completely, to weigh it and confirm it accounts for every last missing atom. Solving the missing baryon problem closes a crucial chapter in our understanding of cosmic structure. It tells us that the ordinary matter, the stuff of stars and life, is all accounted for, but it exists in a state far more elusive and widespread than we ever imagined. A reminder that even the familiar can be hidden in the spaces between everything we see. That hidden fog of ordinary matter forms the backdrop for everything we see, but if we could peer deeper past galaxies and atoms, down to the very foundation of reality itself, we would encounter the final and most profound mystery on our list. The smooth, continuous stage upon which the cosmic drama plays out, the fabric of space and time described by Einstein, may be an illusion. At the smallest conceivable scales, 1,000,000 billion times smaller than an atom, this fabric might shatter into a frothing sea of discrete, quantized fragments. This is the question of the quantum nature of space-time, and its answer would rewrite our understanding of existence from the ground up. Our two most successful theories of reality are locked in a fundamental, century-long conflict. Einstein's general relativity paints a breathtaking picture of space-time as a smooth, dynamic canvas, warping and curving in the presence of mass and energy, creating the force we experience as gravity. It describes the cosmos on the grandest scales with stunning accuracy, from the orbit of Mercury to the bending of light around galaxies. Yet, on the opposite end of the spectrum, quantum mechanics governs the bizarre, probabilistic world of the atom. It tells us that energy, light, and matter are not continuous, but come in tiny, indivisible packets called quanta. This theory is equally triumphant, explaining the stability of atoms, the behavior of semiconductors, and the nuclear reactions that power stars. The problem is, these two masterpieces are written in completely different mathematical languages and based on incompatible principles. General relativity is deterministic and smooth, quantum mechanics is probabilistic and grainy. When their domains collide, in places of infinite density and curvature like the center of a black hole or the first instant of the Big Bang, our equations produce nonsense answers, blowing up into infinities that signal a complete breakdown of physics. It is as if you had one perfect rule book for building continents and another for building sandcastles, but no instructions at all for a grain of sand that is also a mountain. This tells us that our understanding of space-time is incomplete. To resolve the conflict, physicists propose that space-time itself must be quantized. Just as a television screen looks smooth from across the room but reveals its discrete pixels up close, the seamless continuum of space and time may be woven from unimaginably tiny fundamental units. At the Planck scale, distances of about 10 to the negative 35 meters and times of 10 to the negative 43 seconds, the smooth fabric might dissolve into a dynamic, buzzing network of loops, strings, or other geometric atoms. In this view, there is no such thing as a distance shorter than the Planck length, just as there is no such thing as half an electron. Reality has a fundamental resolution. The quest to discover this quantum geometry has given rise to magnificent, though still unproven, frameworks. Loop quantum gravity envisions space-time as a web of intersecting loops where volume and area are quantized, and the Big Bang might be replaced by a big bounce from a previous universe. String theory proposes that the fundamental entities are not point particles but vibrating strings, and that the extra dimensions they require could wrap space-time into a complex, compactified geometry. Other ideas like causal set theory or asymptotic safety offer different paths to the same goal, a theory of quantum gravity. While we lack a specific astronomical phenomenon to point a telescope at, the evidence for this quantum fabric is written in the universe's most extreme events. The seething chaos at the singularity of a black hole, the very first moment of cosmic expansion, the potential for wormholes or the evaporation of black holes via Hawking radiation, all of these are realms where a classical, smooth space-time fails. Understanding them requires us to see the pixels of reality. Future experiments might one day detect subtle signatures, perhaps in the faint whispers of gravitational waves from the earliest universe, or in high-precision measurements that reveal a slight fuzziness in the position of distant stars. This final mystery is not just about the cosmos out there, but about the nature of the stage itself. Is the universe fundamentally smooth or grainy, continuous or discrete? The answer will not change the way planets orbit, but it will redefine what an orbit truly is, transforming our comprehension of reality from a cosmic scale down to its very bedrock. It is the ultimate frontier, a question that asks not what lies within space and time, but what space and time themselves are made of. These 25 cosmic puzzles are not failures of science, but its greatest triumphs. They are the bright, unanswered questions that map the very frontier of human understanding, the places where our most brilliant theories meet the cold, hard wall of observation and find it still standing. From the silent whisper of the wow signal to the colossal, invisible pull of the great attractor, from the ghostly hexagon over Saturn to the missing atoms woven through the void, each mystery is a beacon. It shines a light on a specific crack in our cosmic model, a precise location where we know our map is incomplete. They are not vague curiosities, but targeted challenges, each one demanding a new telescope, a more sensitive detector, or a bolder leap of theoretical imagination. This is how knowledge truly expands, not by polishing what we already know, but by relentlessly pursuing what we do not. Every unexplained flash, every anomalous motion, every geometric perfection in the chaos is a signpost for the next generation of explorers. It tells the engineers where to point the next great observatory, and it dares the theorists to dream equations that can dance where current ones stumble. The journey through these enigmas reveals a universe far stranger, more dynamic, and more creatively violent than we ever imagined from our quiet little planet. It is a cosmos that builds perfect rectangles from dying stars, flings phantom particles with the force of a fastball, and may be woven from a fabric we cannot yet see. This is the thrilling, humbling, and utterly inspiring state of astronomy today. We are not at the end of discovery, we are living in its golden age, surrounded by more profound questions than answers. So the next time you look up at the night sky, see it for what it truly is, a canvas of mysteries. That darkness is not empty, it is filled with puzzles waiting to be solved. Stay curious, follow the news from great observatories and deep space probes, because any day now, one of these enduring riddles could shatter, revealing a new layer of reality beneath. Which of these phenomena keeps you up at night wondering? Do you think dark matter will be a particle or a revolution in gravity? Could the methane on Mars be a geological whisper or something more? Share your thoughts in the comments below. If this journey to the edge of the unknown captivated you, be sure to like this video and subscribe for more deep dives into the universe's greatest secrets. The cosmos is speaking in riddles, and the conversation is just